We often store solutions in a more concentrated form. It's not unlike going to the grocery store and buying frozen concentrated orange juice. Right? It's more convenient because it's in a smaller container. So we have a stock room here, and in the stock room we have stock solutions because they're kept in stock, right? So a stock solution is often more concentrated, and then we can take that more concentrated solution and make lots of different solutions from it, and we don't have to weigh anything out. We can just measure volumes. So we just dilute the stock solution, and so you combine a certain amount of stock solution with water until you get the right concentration. This is very much like making orange juice from concentrate. You take the can of concentrate and you put it in a pitcher, and then you add 3 cans of water and you mix it up, right? So that's diluting a concentrated solution. We use this equation to figure out how much of the stock solution we need and what volume we should dilute it to, because it's not like making orange juice where you're making the same concentration all the time. So this is the equation. M1V1 equals M2V2. It looks like a gas law equation, but it's not. Capital M here stands for molarity. The molarity times the volume of one solution equals the molarity times the volume of the other solution. The reason this works is because if you take, maybe you have a 1 molar solution, 1 mole per liter, and you measure out 5 liters of it. The units come out to be moles. So that's the solute. That's like the yummy stuff in the orange juice concentrate. When you make the orange juice by diluting it, do you lose some of the orange stuff? Do you gain orange stuff? Orange goodness? No, it's the same amount. All you've done is added water, right? You've changed the overall volume, but the orange goodness stays the same. So the moles of solute is like the orange goodness. You're adding water, you're making it less concentrated, but the number of moles stays the same. So M1V1 gives us the number of moles of solute. When we dilute this, the volume goes up and the molarity goes down, but we still have the same amount of solute. So this works only for solution dilution. It's only when you're diluting something. It does not work when you have a chemical reaction occurring. So never use it for titration or stoichiometry or anything like that. It's tempting, and sometimes it works, but oftentimes it doesn't. So just don't do it. And a laboratory safety note: when you're diluting acids, you always add the concentrated acid to the water, never the other way around, because adding water to concentrated acid generates a tremendous amount of heat and can cause it to erupt and splatter you, and acid burns are no fun to deal with. So never add water to concentrated acid solutions. I used to have a hard time remembering that, and so what helped me was thinking about a swimming pool. If you know anything about maintaining a swimming pool, you know that sometimes you have to add acid to the pool to get the pH right. So you're always adding the acid to the water, right? You're never taking the swimming pool and pouring it into the bottle of acid. It's always the acid into the water. And the reason that that's safer is the water can dissipate the heat and it won't get so hot that it boils. We actually had an accident here in the stockroom. It's been years now, but somebody did this the wrong way and concentrated sulfuric acid was dripping from the ceiling as a result. No permanent injuries because the person was wearing their safety equipment, so that was good, but really, really something you don't want to mess around with. So let's do a calculation. How much 6 molar sodium nitrate solution would you use to make 0.585 liters of a 1.2 molar sodium nitrate solution? So this is going to use that equation, M1V1 equals M2V2. What's important here is that you get the correct volume and molarities together. It doesn't matter which one you call 1 and which one you call 2. So we see that 1.2, let me start a little lower. 1.2 molar sodium nitrate goes with this volume. So he says 0.585 liters of this. So those go together. Let's call them 1. So this is going to be molarity 1, and this is going to be volume 1. Just identify them. And then we have 6 molar, 6.0 molar, and so we're going to, well, that's also sodium nitrate. That's a molarity, so we'll call that molarity 2. And then we don't know how much of that, that's going to be volume 2. Any questions? Yes?
Why is the 6 molarity of NaO3 the second molarity?
That's a good question. Why is 6.0 molar the second molarity? Because I started doing the problem backwards. Yeah. It doesn't matter. Some other books use a volume and molarity of concentrated versus dilute, and then it would matter. What I like about the 1 and the 2 is you can choose, they can be either, it doesn't matter, as long as you get them paired up. It's important to have these two paired, but other than that, it doesn't matter. So then I'm going to look at this equation, which thankfully has no fractions, and I need to rearrange it so I can get volume 2 by itself. So I'm dividing by molarity 2 on both sides. So volume 2 is going to equal molarity 1 times volume 1 divided by molarity 2. So these are worked much like the gas law problems. So I've got 1.2 molar up there and 0.585 liters divided by the molarity of the second solution, 6.0. The capital M's cancel out. I have 1.2 times 0.585 divided by 6. 0.117, and the unit would be liters. Should be 2 sig figs, so it'll be 0.12 liters. Any questions? Here's an illustration of how you would go about making a solution like this in the lab. Here we are making 5 liters of a 1.5 molar KCl solution from a 12 molar stock solution. So you do the calculations, and here it's illustrated. 12 moles per liter times 0.625 liters gives 7.50 moles. And the other concentration, 1.5 moles per liter times 5 liters, gives 7.50 moles. The number of moles of solute stays the same. We don't lose any KCl, we don't gain any KCl. All we're doing is adding water. We're changing the volume. So you have to do the calculation, figure out how much you need. So the calculation shows us 0.625 liters of the 12 molar solution. So we're going to put that into a flask, and we're going to add water and to a total volume of 5 liters. Here they're adding water to a more concentrated solution, which is what you should not do with acids. This is not an acid, and so nothing bad's going to happen. Any questions?